You know that tiny little window on an airplane's altimeter? The one with the little numbers inside? It looks like such a minor detail, but it turns out adjusting it is one of the most critical things a pilot does. Today, we are going deep on the brilliant mechanics and the life-saving job of the Kollsman window.
So this whole thing kicks off with what seems like a really small problem. An aircraft owner, Brian Risley, noticed something was off with his plane. It was an air of just 150 feet. I mean, on the ground, who cares? But up in the air, that's a completely different ballgame.
And that really begs the question, right? When you're flying through clouds, trying to avoid mountains, and making sure you don't run into other planes, how much does a 150-foot error actually matter? The answer is a whole lot.
Okay, so let's dig into that. We're going to start with this real-world scenario, because a small error can reveal a much bigger truth about flight safety.
So here was the deal. The pilot would climb, trying to get his altimeter to read, say, 5,000 feet. But to make the needle hit that number, he actually had to climb higher than he should have. This meant his plane was consistently 150 feet above where he thought it was, flying in a dangerous, unassigned pocket of air.
To really get how this happens, we've got to pop the hood, so to speak. We need to look at the elegant and, honestly, surprisingly simple mechanics inside the altimeter itself. Okay, meet the heart of the whole machine, the aneroid wafers. The best way to think of these is like a tiny, sealed metal accordion. This is the part that actually senses you're going up or down.
So here's how it works, and it's actually pretty elegant. As the plane climbs, the air pressure outside gets thinner. The gas that's sealed inside those little wafers expands, pushing them apart. That tiny bit of movement pushes a lever, which turns a set of delicate gears, and that's what spins the needles on the dial. It is pure, beautiful physics in action.
But here's the catch. Those wafers only solve half the problem. See, they react to pressure changes when you climb or descend. But what about pressure changes just from the weather moving in? Well, for that, we need the star of our show.
This is it, the Kollsman window, named after its inventor, Paul Kollsman. Its job isn't to measure your altitude change. Its job is to tell the altimeter what the baseline air pressure is at sea level right now, wherever you happen to be. It basically anchors the entire instrument to the reality of the local weather.
So let's break this down, because this is the key. The aneroid wafers work automatically, right? They just sense you're moving up or down. But the Kollsman window is manual. The pilot has to actively tell it what's going on with the local weather. One reacts to where you are vertically, and the other calibrates for what the atmosphere is doing all around you.
Now this is the part that is just wild. When a pilot turns that little knob, they are not just spinning some numbers in a window. No, they are physically rotating the entire delicate internal assembly, the wafers, the levers, the gears, the whole shebang. You are literally moving the whole machine inside its case to line it up with the correct needle position. It's amazing.
Okay, so let's put this all together and see why this isn't just a cool piece of engineering. This is a critical safety lesson, where getting this calibration right is quite literally a matter of life and death.
This is a golden rule in aviation. You gotta burn this into your brain. For every 1-inch change in barometric pressure, an altimeter will change its reading by about 1,000 feet. Remember that. 1 inch equals 1,000 feet. So let's set up a scenario. Picture our pilot. They take off from an airport where the weather is nice, a high-pressure zone. Let's call it 30.00 inches of mercury. They set their Kollsman window to that number, they climb up to 2,000 feet, and everything is perfect. The instrument says 2,000 feet, their true altitude is 2,000 feet. All good. But as they fly along, they enter a different weather system. A storm is moving in, creating a low-pressure area where the new sea level pressure is 29.00 inches. And here's the critical mistake. They forget to update their altimeter. Because those wafers inside are still sensing the same pressure relative to the old, incorrect setting, the needles on the dial haven't moved an inch. It still says 2,000 feet. But here is the terrifying reality. The pressure dropped by 1 full inch, which means their aircraft is now actually flying at only 1,000 feet above the ground, even though their instrument is confidently telling them they're safe at 2,000. They are 1,000 feet lower than they think they are, flying blind towards whatever might be down there.
And this is where one of the oldest and most important sayings in flying comes from. When you fly from a high-pressure area to a low-pressure area without updating your altimeter, your real altitude is going to be lower than what your instrument says. From high to low, look out below.
So you might be asking, how do pilots keep this from happening? How do they avoid this dangerous illusion? Well, they have to constantly, and I mean constantly, anchor their instrument back to the real world.
Before they even take off, pilots get the local pressure setting from automated weather broadcasts, something called ATIS. In the air, they can just ask air traffic control for it. A good rule of thumb is to get a new setting about every 100 miles or so. And if all else fails, a pilot can sit on the runway, look up the airport's known elevation, and just spin the knob until the altimeter reads that number. That mechanically dials in the correct pressure. And even with all this precision, there's still a little wiggle room. On the ground, a properly set altimeter is considered good to go if it's within 75 feet of the actual field elevation. This just goes to show how sensitive these things are, and it really puts that 150-foot error we started with into perspective, right? That's way out of spec and a clear sign something is wrong. When you step back and think about it, it's just a simple knob, but it connects this delicate, beautiful mechanical device to the vast, invisible forces of the atmosphere. It makes you wonder, doesn't it? What other simple calibrations, in all the technology we rely on every day, are the only thing standing between us and potential disaster?